So for section 1.4, we're going to talk about inverse functions and what criteria a function needs to meet in order to have an inverse. Because not all functions are created equal and not all functions have inverses. So let's take a look. So friendly reminder that when we define a relation, we can define that relationship as a set of ordered pairs, a table, a graph, an equation, or a rule. This is the type of relation we're going to be working with the most. That relation is a function if for each distinct value of x, there's only one y value. And I talked about this in section 1.1 by going over a vending machine. Remember, you push the button, you get one thing out. You can't have one button going to two different foods. If you do, the vending machine's going to break, and then it's not a function. Or not a functioning vending machine. Remember, in order for something to be a function, it has to pass the vertical line test. So here we have a linear equation that passes the vertical line test, a parabola. Things that don't pass the vertical line test are circles, this rotated absolute value function, right? These are not functions because they do not pass the vertical line test. We have another special type of function. A function is one-to-one if for all the elements a and b in the domain of f, a doesn't equal b implies f of a doesn't equal f of b. This is a very complicated way of saying that each x has exactly one y value. That means that each button in our vending machine only goes to one food. This is a function, but what's nice about this function is it's one-to-one. Okay? We can also have a function that's not one-to-one, and that would be if we had C going to chips and D going to chips. The vending machine's still going to work. Okay? The vending machine's still going to work. You push C, you get out chips. You push D, you get out chips. But it's not one-to-one because each x doesn't have exactly one y value. Let's go ahead and check if these relations, which are functions, are one-to-one. So here I have my x values and my y values. I like to make a nice little table. My x values are 1, 4, and -1. My y values are 2, 5, and -2. I have 1 going to 2, 4 going to 5, 1 going to -1. Yep, this is one-to-one. Let's take a look at relation G. My x values are -3, -2, -1, and 0. My y values are 5, 5. Now remember, we're working on a number line. Just because it shows up twice, we don't write it twice. 4 and 1. I have -3 and -2 go to 5. -1 go to 4, and 0 go to 1. Is this a one-to-one function? No, this is just a function, right? It's not one-to-one because -3 goes to 5 and -2 goes to 5. All right, last but not least, I have relation H. So x is -1 and -2, y is 0, 2, and 1. And I have -2 going to 2 and 1, and -1 going to 0. Is this one-to-one? No, this is not one-to-one, but it is a function. Now, in order to prove that a function is one-to-one, we need to show that f of a equals f of b gives us the same result. So the first thing I want to check is this a function? I have -4x plus 12. That graph is going to look like a line, so it is a function. So I have f of a equals f of b, and I'm going to substitute in a and b to my equation. So I have -4a plus 12 equals -4b plus 12. I subtract 12 from both sides. I get negative 4a equals negative 4b. I divide both sides by negative 4. I get a equals b. Boom. That is a function. Oops, zoomed in. Next, let's take a look at my second function. I have f of x equals 2x squared minus 3. This is a quadratic function. Its graph is going to look like a parabola. But we already know that parabolas might not be 1 to 1, right? Because if I have negative 1 squared, that's the same as 1 squared. So let's take a look at what happens. So I have f of a equals f of b. So I have 2 times a squared minus 3 equals 2 times b squared minus 3. And I'm going to go ahead and add 3 to both sides. That gives me 2a squared equals 2b squared. We divide both sides by 2. I get a squared equals b squared. I have to take the square root of both sides. But when I get the square roots, I get plus or minus a equals plus or minus b. This means I could have positive a equal to negative b. And that is not the same thing as a equals b. So this is not a one-to-one function. And we've got an easy way to test whether something is a one-to-one function. And that's the horizontal line test. A function is one-to-one if every horizontal line intersects the graph at one point. So the first thing we always want to do is check the vertical line test to make sure they're a function. But then we can come on in with a horizontal line test, and that'll tell us if it's one-to-one. You can see here this parabola, and all parabolas are going to fail the horizontal line test because I've got two x values to this one y value over here. So horizontal line test is how we're going to check whether or not something is a function. If a function has an inverse, so if it's one-to-one, we can calculate its inverse. And we can check to see if functions are inverses by taking their combination. Okay? So if I have two functions f and g, and I take f composed with g, and I get that equals x, and I take g composed with f, and I get that equals x, then those two functions are inverses. And we could rewrite g as f inverse of x, which we read as f inverse, but it just tells us that this function is the inverse of f. So let's go ahead and determine if the following two functions are inverses. And in order to do this, we need to check function composition both ways. If you need a refresher on function composition, feel free to check out section 1.1 videos where I do a couple examples of function composition. So I'm going to go ahead and take f composed with g of x. That means I'm going to plug in g for x. That means I'm going to take, for f of x, I've got something cubed, so I'm going to take g of x plus 1 cubed minus 1. Well, cube roots cancel out cubes. Cubes cancel out cube roots. So that leaves me with x plus 1 minus 1, which is x. Awesome. Does that mean that these two functions are inverses? No, not yet. I have to check both ways. So I'm going to take g composed with f of x. That's g of f of x. And now I'm going to substitute in f of x in for g. So I have for x in g. So I have the cube root of x cubed minus 1 plus 1. That means I have the cube root of x cubed plus 1 minus 1, which means I have the cube root of x cubed. Well, cube roots cancel out cubes, so I'm left with x. So because f composed with g and g composed with f both gave us x, that means that yes, these are inverses. And we could rewrite g of x as f inverse of x. So after the negative 1 is read f inverse. All right, let's check out another example. I have f of x equals negative 3x plus 12, and g of x equals negative 1/3 x minus 12. So let's take f composed with g first. So I'm going to take negative 3. Remember, I'm plugging g of x in for x. Negative 3 of negative 1/3 x minus 12 plus 12. That gives me, I have to distribute negative 3 times negative 1/3. That gives me a positive x. Okay, that's a good sign. But then I have negative 3 times negative 12. That gives me a positive 36 plus 12. So I get x plus 48. Because I did not get x, I know that these functions are not inverses, so we don't need to check the other direction. Let's try one more. I'm going to take f composed with g of x. So we plug in g of x in for x in f. So I have 2 times 1/2 x minus 2 plus 4. That gives me x minus 4 plus 4, which is x. Okay, I need to check the other direction. If I take g composed with f of x, that gives me 1/2 2x plus 4, because I'm substituting f of x in to g, minus 2. That gives me x plus 2 minus 2, so I get x. So yes, they are inverses, and I can rewrite g of x as f inverse of x. Now, what if I wanted to find the equation for the inverse? What if I wasn't given the equation? Well, you can find the equation for the inverses by changing x and y, solving for y, and replacing y with f of x. So let's take an example. I have y equals 2x plus 5. Step 1, we're going to interchange our x and y. So I have x equals 2y plus 5. I'm then going to go ahead and solve for y. So I'm going to subtract 5 from both sides. That gives me x minus 5 equals 2y. Then I'm going to divide both sides by 2. So I have 1/2 x minus 5/2 equals y. So I can rewrite this step 3 as f inverse of x, because that's what it wants us to do, is 1/2 x minus 5/2. So this is how we go about finding the inverse. Note, it has to be a one-to-one function in order to find its inverse. So let's take a look at another example. What if I'm given y equals x squared plus 2? This graph is a parabola. It's a function, but is it one-to-one? No. So the inverse does not exist because it's not a one-to-one function. Okay, let's take a look at x minus 2. This is a cubic. The cubic equations, whose shape is kind of like this, pass the horizontal line test and the vertical line test? Yeah, they do. So we can go ahead and find the inverse. I'm going to do that by first switching x and y. Then I need to solve for y. I'm going to do that by taking the cube root of both sides, because cube roots cancel out cubes. So I have the cube root of x equals y minus 2. I'm going to add 2 to both sides. So I have the cube root of x plus 2 equals y. I then need to rewrite this with f of x. So I have f inverse of x equals the cube root of x plus 2. So here we've found the inverse to our cubic, and it's a cube root. Some important facts about inverses. For every function that's one-to-one, it has an inverse. Okay? That and the domain of one is the range of the other, right? One sends x to y, the other sends y to x. It undoes each other. That's why when we compose them, we get x. So that's being said, if a point AB lies on a function, then the point BA lies on the other. And these graphs are reflections of each other across the y-axis. This isn't symmetry, these are just reflections.